Ever feel like you're stuck in an information black hole? Well, get ready for a different kind of black hole deep dive today. One where quantum physics throws a wrench into the cosmic machinery and things get seriously weird.
And we're talking seriously small black holes here, the kind that might have formed right after the Big Bang.
Primordial black holes, right? I've heard whispers about these, but they're not exactly the headline-grabbing monsters that usually come to mind.
Definitely not those celebrity supermassive ones. Think of these more like the micro-influencers of the black hole world, tiny but potentially mighty.
Okay, I'm intrigued. So what's the big deal with these mini mysteries? What secrets are they hiding?
Well, there's this fascinating new paper by Abraham Loeb, and he suggests that these primordial black holes, these PBHs, might not be living up to their reputations as, the ultimate cosmic vacuum cleaners.
Wait, really? I thought black holes were all about insatiable hunger, devouring anything that gets too close.
That's the thing, it might not be that simple, especially at these incredibly small scales. It's not just about gravity pulling things in, it's whether those things can even fit inside the black hole to begin with.
Hold on, how can something as dense as a black hole have a size limit? Isn't their gravity supposed to be inescapable?
You'd think so, right? But that's where the weirdness of quantum mechanics crashes the party. See, at these tiny scales, the rules of the game change.
Quantum physics, always breaking the mold. I should have known better than to underestimate its ability to turn things upside down.
It's notorious for that, but in this case, it's seriously cool. See, objects, even the atoms a black hole might try to eat, don't just act like simple points in space anymore. They also have wave-like properties.
Wave-like, you mean, like they're spread out, not just in one specific spot.
Exactly. It's like they have a certain probability of being in multiple places at once. So instead of a black hole with a gaping maw just waiting to gobble things up, we're dealing with something a lot more nuanced.
So it's less about a black hole with a giant mouth and more like, what, trying to grab onto a cloud?
You're getting the idea. Now, picture this. A black hole so tiny, so unbelievably small, that its point of no return, what we call the Schwarzschild radius, is about the size of a single hydrogen atom.
A black hole the size of an atom, that's almost unfathomably small. I'm having trouble wrapping my head around that.
It's mind-boggling, right? Just stick with me, because this is where it gets good.
Okay, you've got my attention. Lead the way.
So imagine this tiny black hole encounters a hydrogen atom. We can't think of that atom as a tiny marble just falling straight in. Because of quantum mechanics, that atom is more like a fuzzy cloud, spread out over a space bigger than the black hole itself.
Okay, now I see the dilemma. It's like trying to stuff a giant blurry beach ball into a shot glass. No wonder these primordial black holes might be struggling to snack.
And Loeb, he's great at explaining these complex ideas. He takes it a step further with this brilliant analogy of a black hole as a prison.
A prison. I'm listening.
So he compares this whole scenario, a small black hole trying to capture an atom, to trying to force a large, uncooperative prisoner into a tiny, cramped cell.
Okay, I love where this is going.
And just like a prison has doors and guards and walls, the world of quantum mechanics, it's got its own set of rules, its own quirks that make it incredibly difficult, even for a black hole, to capture its prey.
So are we saying these mini black holes are doomed to a life of cosmic hunger pangs? Forever eyeing a meal, but never quite able to overcome that quantum fuzziness?
It's a fascinating question, and Loeb, he really dives into the potential consequences of this, what he calls quantum suppression of accretion. And what he found, it's pretty wild.
Okay, now you got to give me the rundown. How slow are we talking here? Like slower than a snail in a traffic jam?
Think even slower than that. Imagine that snail, right? But instead of crossing the garden, it's trying to cross the entire observable universe.
Whoa, okay, that's a long, slow crawl.
That's the kind of time scale we're dealing with here. Some of these primordial black holes, Loeb's calculations, show that they would barely gain any mass, like almost none, over billions of years, even with all that time since the Big Bang.
So let me get this straight. We could have these ancient black holes out there, older than time itself, but still tinier than an atom. All because quantum mechanics put a stop to their growth spurt.
You got it. It really makes you appreciate the mind-blowing scale of things, right? The universe's biggest and smallest extremes, all tangled up together.
Talk about a cosmic paradox. But wait, you said this wasn't even the whole story, right? There's more to this black hole saga?
Oh yeah, we're just getting started. Remember Hawking radiation?
Right, Stephen Hawking. Black holes aren't completely one-way streets. They actually kind of evaporate over time, right? Even though nothing's supposed to escape a black hole's grip.
Exactly. That tiny bit of energy and mass that leaks out, that's Hawking radiation. But here's the kicker. The smaller the black hole, the faster it evaporates.
So not only are these mini black holes struggling to eat because of all that quantum fuzziness, they're also potentially shrinking at the same time.
Now you're seeing the whole picture. It's like this cosmic tug of war going on, gravity trying to pull everything in, but quantum mechanics and Hawking radiation, they're pushing back.
What a showdown. Okay, but are there any other contenders in this cosmic battle royale? Any other factors that could tip the scales?
Loeb, he throws in one more intriguing detail. What if these primordial black holes had an electric charge?
Wait a minute, I thought black holes were all about gravity. How can they have an electric charge?
So picture this. Our tiny black hole, right, maybe through some quantum shenanigans, it manages to snag the proton from a hydrogen atom.
Okay, I'm following.
But the electron, with its wave-like nature, it's too spread out, too fuzzy, and it gets left behind.
So the black hole makes off with the positive charge of the proton, leaving it with a net positive charge, like a cosmic thief.
You got it. And that charge, it throws a whole new wrench into the works. Now, suddenly, this charged black hole, it might have an easier time attracting a negatively charged electron to neutralize itself.
Wow, so now we're talking about a three-way dance-off. Gravity, quantum mechanics, and now electromagnetism all caught in this cosmic tango.
And this is just scratching the surface. It gets even wilder from here.
I bet it does. I'm already blown away. Black holes the size of atoms, maybe the answer to dark matter, possibly evaporating, and now they might even be electrically charged. The universe, I swear, it never plays by the rules.
And that's what makes it so much fun to explore. The coolest part is we're just starting to unravel these mysteries. While we learn about primordial black holes, it could totally change how we understand the universe's most fundamental forces.
It's wild to think something so tiny, these mini black holes, could be connected to such huge mysteries. Where does this all lead? What are the big takeaways from diving into all this?
I think the biggest whoa moment here is the link to dark matter. We've been searching for decades, right, trying to figure out what this invisible stuff is that makes up most of the universe's mass.
Oh, right, the universe's biggest hide-and-seek game.
Exactly. And these primordial black holes, especially if they haven't grown much because of those quantum effects we talked about, they're looking like a pretty good contender.
So these tiny black holes, they could be all around us, and they might be the missing piece of the puzzle. Like we've been searching for this phantom, and it's been these little quantum specks all along.
It's a pretty cool idea, right? And what's even more exciting is that Loeb's research, it gives us a way to maybe test this out.
Oh, how do we do that?
He thinks that if we could actually find and observe one of these primordial black holes up close, one that's maybe the mass of an asteroid.
So it's still tiny in the grand scheme of things.
Oh, yeah, definitely. But he says it would be like looking directly into the world of quantum gravity.
Hold on, quantum gravity. Now we're talking about the holy grail of physics, right? Where Einstein's theories about gravity finally meet the weirdness of quantum mechanics.
You nailed it. It's the ultimate goal, trying to unify those two. And Loeb thinks these primordial black holes, if we can just find them and study them, they might hold the keys to unlocking some of those secrets.
That's incredible. All because we dared to ask how a tiny black hole could eat in a universe run by quantum mechanics. Makes you feel pretty small, huh?
It really puts things in perspective. The universe's biggest mysteries might be hidden in the most unexpected places. It's all about connecting those dots.
It really is. And on that note, I think it's time to wrap up this deep dive. It's been a wild ride through black holes, quantum fuzziness, and the endless wonders the universe throws at us. Thanks for exploring with us. And remember, even the smallest things can lead to the biggest questions.